Greetings of the day to all of you. Today we are going to discuss third type of variable impedance series compensator, or third type of series compensator which is called thyristor controlled series compensator. I will write here thyristor controlled series compensator. It's also written as TCSC, that is thyristor controlled series compensator. In some literature it is read as thyristor controlled series capacitor, but instead of calling it thyristor controlled series capacitor, the most generalized name is series compensator. It's thyristor controlled series compensator, TCSC. Because it does not behave as variable capacitance only, we can make it to behave as a variable inductance also. Okay, you will learn how we can make this compensator to act as a variable capacitance and also to act as a variable inductance. Okay, so actually this thyristor controlled series compensator, TCSC, basically it comprises of a capacitance which is shunted by a TCR, something like this. Let me first of all draw, then I will explain. So this is the transmission line. This is transmission line current I. Now this is our, what is this? This is the thyristor control reactor, TCR, we know. Because TCR comprises of bidirectional switch in series with an inductance, a fixed inductance. So this is TCR. And this is a capacitor, okay? So the current drawn by this TCR is, let's call that IL, which is a function of alpha, as we already know. So the total transmission line current is I, therefore current flowing through the capacitance, IC, which is also a function of alpha, is equal to I plus IL alpha. By Kirchhoff's current law, current in this branch is this current plus this current. So it is I plus IL alpha, and that is the capacitive current. And the voltage across capacitor is, for example, VC. So therefore, by having alpha control of this thyristor controlled reactor, TCR, by controlling its inductive current, and hence by controlling its reactance with the help of alpha control, delay angle control, we can make it a variable capacitor. We can in fact make the capacitor to be more than the actual its capacitive reactance can be made higher than the normal capacitive reactor, because this L and C, they are basically parallel LC circuits. And by controlling the magnitude of current through this TCR, and hence by controlling the TCR reactance, we can make the capacitive reactance higher, or we can make it lower. Okay, we can make it a variable capacitive reactance. Okay, and also at certain at certain values of alpha, we can make it to behave as the whole combination can be made to behave as a variable inductance. Okay, so for certain range of alpha, this whole assembly TCSC can be made to function as a variable capacitance, variable capacitive reactance, and for some other range of alpha, delay angle, this combination TCSC can be made as a variable inductor. Okay, so therefore it can be made to behave as a variable capacitance or a variable inductance, depending upon the range of delay angle alpha of this TCR. Okay, practically we do not have one TCSC in series with transmission line. We have many TCSC units connected in series. It's something like this. For example, this is one capacitor, this is second capacitor, then this is, so we can have many capacitances, many these TCSCs in series, something like this. Similarly, then we have another TCSC. for example, switch S1, S2, Sn minus 1, Sn. This is capacitor C1, this is capacitor C2, so on, Cn minus 1 and Cn. Okay, so therefore TCSC basically is a series combination of many TCSC units. For series compensation of a transmission line, many TCSCs are connected in series like this. So this is practically how it is connected in the system. The main aim or main objective of TCSC, as I have already told you, is to provide a variable compensator, variable capacitance and variable inductance. How does it? Because you can see, it's basically it behaves as a parallel LC circuit. Whenever this TCR switch is turned on, the capacitance, there is an exchange of current, a flow of current within this parallel LC circuit. So for certain range of delay angle of this TCR, this parallel LC circuit will cause a larger voltage across this capacitance, so it can increase the capacitive reactance. Okay, so it can increase the capacitive reactance. What is the normal capacitive reactance? Normal capacitive reactance is 1 by omega C. But this capacitive reactance can be made more than this normal value by this parallel LC circuit by adjusting the delay angle of this TCR and making a certain amount of current to flow in this LC circuit and making XC greater than 1 by omega C. Okay, so it can be made a variable capacitive reactance. And for some different range of delay angle of this TCR, the same combination can act as a variable inductance. Okay, you will learn that with the help of when we draw the characteristics, when we draw the graphical representation, and I show you the variation of TCSC, this reactance with alpha. You will understand how a TCSC acts as a variable capacitive reactance for one range of delay angle, and it acts as a variable inductive reactance for a different range of delay angle. So therefore, main aim or main objective of TCSC is to make it a variable compensator, a variable capacitive reactance for one range of delay angle and a variable inductive reactance for a different range of delay angle. Okay. Now XC, that's capacitive reactance, is generally 1 by omega C, and XL, that is reactance of TCR, it is a function of alpha. This is not a function of alpha, right? I mean, if you take capacitance alone, its capacitive reactance is not a function of alpha, but the inductive reactance of this TCR branch is a function of alpha, that we already know. So therefore, this acts as a parallel LC circuit, and acting as a parallel LC circuit, the TCSC reactance is given by TCSC reactance is mathematically given by TCSC reactance becomes a function of alpha. So it is written as XTCSC, which is a function of alpha. It is, since these two are parallel, so it is XC into XL alpha divided by XL alpha minus XC. Because it is a parallel LC circuit, the capacitive reactance is XC, the reactance of TCR inductance is XL, which is a function of alpha. So the total TCSC reactance is XC into XL alpha divided by XL alpha minus XC, right? And what is this XL alpha? We know that the susceptance of a TCR, I should write here TCR susceptance. We have already got this equation in one of very earlier classes. BL, which is a function of alpha, we already know that is equal to 1 by omega L times 1 by pi minus 2 by pi alpha minus 1 by pi sine 2 alpha. You should remember this equation on the tip of your tongues. We already know, we have derived it in one of the earlier classes when we were discussing the operation of a TCR. The TCR susceptance is this. So therefore, what is TCR reactance? Reactance is reciprocal of susceptance. TCR reactance XL, which is a function of alpha, is equal to 1 by BL. Okay, and that is given by, so reciprocal of whole this is omega L times pi minus 2 alpha minus sine 2 alpha by pi. That is the reciprocal of this. And what is omega L? Omega L is XL. So therefore, reactance of this TCR in this TCSC is a function of alpha, and it is given by this equation XL, which is basically omega L, times pi minus 2 alpha minus sine 2 alpha by pi. So it clearly shows that this TCR reactance is a function of alpha. It's not fixed, it is a function of alpha. Where capacitive reactance is fixed. Capacitive reactance alone is fixed, and that is given by, what is this capacitive reactance? That's given by 1 by omega C. But inductive reactance or TCR reactance is not fixed. It's a function of alpha, and it is given by this equation. So I hope this is clear. Okay, now let me draw this again. This is thyristor T1, this is thyristor T2, this is L, this is transmission line current I, the voltage across capacitor is VC, this TCR current is IL, which is a function of alpha, and capacitive current is IC alpha, which is equal to this current plus this transmission line current plus TCR current, I plus IL alpha. Okay. Now, if we do the alpha control of this TCR, and hence control its inductive reactance, control the current IL alpha, and hence control the inductive reactance, then we can make this XL variable. I mean, this XL will be XL, which is a function of alpha. We can make it vary for a range of alpha 0 degrees to 90 degrees. For example, if alpha is 0 degree, then we know that TCR is in full cover. We know the range of delay angle control is 0 to 90 degrees, or with respect to the peak of the voltage is 90 to 180 degrees. So let us call it 0 to 90 degrees. Let's say it is 0 to 90 degrees. For alpha equal to for alpha equal to 0 degrees, your TCR is in full conduction. And what is its inductive reactance? Its inductive reactance is omega L. So it has maximum inductive reactance. Sorry, not maximum inductive reactance, minimum inductive reactance, and that is omega L. And as you increase a delay angle from 0 degree to 90 degrees, we know that the TCR reactance increases because it is a function of alpha. And when alpha is equal to 90 degrees, the TCR is in off state. We know that for alpha equal to 90 degrees, TCR turns on, off. And when it turns off, what is its inductive reactance? Its inductive reactance is infinite. Okay, only when its inductive reactance is infinite, it will not conduct any current, and that means open circuit. So for alpha equal to 0 degree, TCR is in full conduction, and its inductive reactance is minimum, that is equal to omega L, which is 2 pi FL. And as you increase alpha from 0 to 90 degrees, the inductive reactance increases till you reach alpha equal to 90 degrees, at which inductive reactance is infinite, because at alpha equal to 90 degrees, TCR blocks the current. It does not allow any current to flow. It acts as an open circuit, and inductive reactance is infinite. So therefore, by alpha control, it is quite clear that the reactance of TCR can be made variable. Okay. Now, as this TCR reactance is made variable, it is varied as XL alpha is varied, say, from maximum value to minimum value, to some minimum value. From maximum value, what is maximum value? Maximum value is when XL is infinite, corresponding to alpha equal to 90 degrees, to lower value. Corresponding to alpha equal to 90 degrees, TCR reactance is infinite. And as you decrease alpha from 90 degrees towards 0 degree, the TCR reactance decreases. So therefore, if you do the alpha control, initially alpha is 90 degrees, for which TCR reactance is maximum, it's infinite, and then you decrease alpha from 90 degrees towards 0 degree, I mean to a lower value from alpha equal to 90 degrees to some lower value, what happens to the TCR reactance? TCR reactance decreases from maximum value to some lower value. Okay, so what will happen to TCSC capacitive reactance? Overall TCSC capacitive reactance, TCSC capacitive reactance will change. I will write here TCSC capacitive reactance varies from minimum value, which is Xc equal to 1 by omega c, and to higher value, and thus increases the degree of series compensation. The degree of series compensation. We know the degree of series compensation is given by this equation, K is equal to Xc by X. Until, let me complete this sentence, then I will explain. Until parallel resonance occurs. Parallel resonance occurs at or when XL alpha is equal to Xc and X TCSC, which is a function of alpha, becomes infinite. See, try to understand this. Let us assume that TCR is operated at alpha equal to 90 degrees. We know that at alpha equal to 90 degrees, the TCR does not conduct, it blocks, and its inductive reactance is maximum. It's maximum, that's infinite. Okay, and when its inductive reactance is maximum, so no current flows through this TCR because it is in the blocking state, and all the transmission line current flows through the capacitance, series connected capacitance, and therefore capacitance will have minimum capacitive reactance value. And what is that? That is simply equal to Xc equal to 1 by omega c. When all the current flows through the capacitance, this capacitance offers a reactance which is minimum reactance, capacitive reactance 1 by omega c. That we already know. And then what we do, we decrease the delay angle of this TCR from 90 degrees towards some lower value. As we decrease delay angle from 90 degrees towards the lower value, what happens to the this TCR reactance? This TCR reactance now decreases from maximum value, which was infinite to some lower value. And since L and C they form a parallel resonant circuit, what happens to the overall capacitive reactance or overall TCSC reactance? Overall TCSC reactance increases. Okay, as inductive reactance decreases, L and C are in parallel, the overall capacitive reactance increases, or overall TCSC capacitive reactance increases, being a parallel LC circuit. And when Xc increases, okay, then what happens to the degree of series compensation? That increases. So your Xc, which is a function of alpha, it becomes greater than the normal Xc. It increases. Okay, at alpha equal to 90 degrees, Xc is equal to 1 by omega c, and as you decrease alpha of TCR from 90 degrees to lower value, its inductive reactance also decreases. And since C and L are parallel resonant circuit, it's a parallel circuit, then because of the parallel LC circuit, the overall capacitive reactance increases, and it becomes greater than the minimum capacitive inductance, becomes greater than 1 by omega c. And when Xc increases, we know that degree of series compensation is given by Xc by X. So and Xc increases, the degree of series compensation increases until when XL alpha becomes exactly equal to Xc. And we know that from basic circuit theory, we know that in a parallel LC circuit, when XL is exactly equal to Xc, a parallel resonance occurs. And when parallel resonance occurs, TCSC reactance becomes infinite. We know that in a parallel LC circuit, when resonance occurs, the overall impedance of the circuit becomes infinite. Okay, so starting from alpha equal to 90 degrees for TCR, the TCSC reactance is minimum capacitive reactance, that is equal to Xc equal to 1 by omega c, and then decreasing alpha from 90 degrees to lower value, the TCR reactance decreases, and since L and C forms a parallel LC circuit, the overall TCSC capacitive reactance increases. It becomes greater than XC until parallel resonance occurs when XL alpha is equal to exactly XC, and when this happens, the TCSC total reactance or capacitive reactance becomes infinite, okay, which is again undesirable thing. And if we decrease alpha further, okay, beyond when this parallel resonance occurs, it occurs at a particular value of alpha. It may be alpha equal to 40 degrees, 30 degrees, we don't know, and for which XL alpha is equal to XC. As alpha is decreased further, what happens to the TCR reactance? TCR reactance XL alpha further decreases, and when it further decreases, overall TCSC reactance becomes now inductive. So TCSC reactance now, earlier up to the resonance it was capacitive. Now the effective TCSC reactance, which is a function of alpha, it becomes inductive in nature. Inductive in nature beyond resonance. Beyond resonance. So beyond, that means beyond XL alpha equal to XC. As alpha is further reduced, XL alpha further decreases, okay, and then this circuit, LC circuit, behaves as an inductive circuit. So that means starting from alpha equal to 90 degrees up to some lower value of alpha, the overall TCSC reactance behaves as a capacitive reactance. It increases from minimum value of 1 by omega C to infinite value when parallel resonance occurs, when XL alpha is equal to XC. So infinite capacitive reactance, beyond which, as alpha is further reduced, XL alpha further decreases, and your TCSC now behaves as inductive circuit. It becomes inductive in nature till alpha is equal to 0 degree, and when alpha is equal to 0 degree, okay, this TCSC is full, it's in full conduction, and when it is in full conduction, its reactance is minimum, and that is equal to XL equal to omega L. It's the minimum reactance. So at that time, this TCSC, it behaves in the inductive region till alpha is equal to 0 degree. So therefore, this alpha, that is TCR delay angle, we can divide it into two ranges. One is 90 degrees to some lower value. Okay, this alpha can be divided into two ranges. One is alpha which varies from 90 degrees to some lower value. Let's call that alpha C lim. Lim means lower limit of alpha. And during this, your TCSC reactance, you have just now few moments back seen, it is capacitive in nature. At alpha equal to 90 degrees, TCSC reactance is minimum, that is equal to 1 by omega C. As alpha is decreased from 90 degrees to alpha C lim, your TCSC reactance, becomes more and more capacitive. Okay, it goes on increasing till XC lim. If alpha is decreased below XC lim, then parallel resonance will occur. Okay, and the TCSC reactance will become infinite. And another range of alpha is some lower value limit, alpha L lim. Let's call that alpha L lim to 0 degree. This is 90 degrees to alpha C lim. Your TCSC reactance is capacitive, and from alpha L lim, I mean resonance ke baad, some lower value of alpha to 0 degree, your TCSC behaves as inductance, and XTCSC, which is a function of alpha, it becomes inductive in nature. So therefore, we can make TCSC to behave as a variable capacitance, capacitive reactance, or as a variable inductive reactance if we operate it within these two ranges of alpha. If you operate your TCSC in this delay angle range, 90 degrees to alpha C lim, then it will behave as a variable capacitive reactance. And if you operate it in this delay angle range, alpha L lim to 0 degree, it will operate as a variable inductive reactance, inductive region. So hence we can make it operate as a variable capacitance or as a variable inductance depending upon the delay angle range. Okay. So So therefore, let me show you or explain it with the help of the diagram, the graph. The graph is very simple. This is alpha delay angle along this axis, and along this axis we have X TCSC reactance, which is a function of alpha, and this is 0, for example. In the center, I will show you a resonance. Let me first of all draw, then I will explain. Let us suppose we operate our TCSC with TCR at alpha equal to pi by 2, 90 degrees. And we know that when alpha is equal to 90 degrees, the TCR inductive reactance is infinite. No current flow. So TCR is in the off state, no current flows through the TCR, all the current flows through the capacitance, and capacitive reactance is minimum. Okay, this is the, for example, this is capacitive reactance. Okay. And then as alpha is decreased from pi by 2 to some minimum value. So this is the minimum value. Let's call this delay angle as alpha C lim. Minimum limit of it may be 20 degrees, 30 degrees, 40 degrees, we don't know. And as you decrease alpha from pi by 2 to this alpha C lim, delay angle from 90 degrees to alpha C lim, some lower value, we know that TCR reactance decreases, inductive reactance decreases, and since L and C are in parallel, overall TCSC reactance increases. It is capacitive in nature and it increases like this. It goes on increasing as alpha is reduced till you reach alpha equal to alpha lim. At alpha equal to alpha C lim, it has maximum capacitive reactance, and if you operate it from alpha C lim to this point, at this point resonance occurs, and at this point I will write here a resonance occurs. And when resonance occurs, alpha XL alpha exactly is equal to XC, and current becomes infinite, as you can see. Okay, infinite. Sorry, this capacitive reactance becomes infinite, not current. Capacitive reactance tends towards the infinity. So therefore, it's not advisable to operate your TCSC for a delay angle below alpha C lim, because as you decrease your delay angle of TCR below alpha C lim, you are reaching very close to resonance condition. This is the resonance condition, and at resonance condition, XL alpha is equal to XC, and TCSC reactance becomes infinite. As you can see, it tends to become infinite. So therefore, this is the minimum delay angle if you want to operate your TCSC as a variable capacitance, as a variable capacitive reactance. So this is therefore the capacitive range. So this is, I will write here, this is the capacitive range or capacitive region of operation. And what is the delay angle in this range? Delay angle range is alpha C lim less than or equal to alpha less than or equal to pi by 2. Pi by 2 to this lower value of pi by 2 is the higher value of alpha, alpha C lim is the lower value of alpha. So it is alpha C lim less than or equal to alpha less than or equal to pi by 2. Okay. Then if you operate your TCSC within this range, this is called prohibited zone. This is prohibited, highly prohibited. This region is prohibited region. I will write here, it is prohibited region. Why is it prohibited region? Because the range of alpha within this region makes this condition true. XL alpha equal to XC, and resonance will occur. And when resonance occurs, it becomes a parallel LC circuit. The reactance becomes infinite. So therefore, we should never operate our TCSC within this range of alpha. If this is alpha C lim, let us call this alpha L lim. This is alpha L lim. This delay angle. Now, if you decrease your alpha below this resonance condition, you are decreasing alpha, you are reaching XC lim, you go on decreasing alpha. If you jump from XC lim to XL lim, So for example, this may be 45 degrees, this may be 50 degrees. So then this TCR reactance will further decrease. And now your circuit, instead of behaving as a capacitive reactance, it will behave, overall effect will be inductive. It will behave as an inductive reactance. Okay, and its inductance will go on increasing. Okay, I mean within this range, inductive reactance is infinite, and then this inductive reactance will go on decreasing, not increasing, it will go on decreasing till you reach alpha equal to 0 degree. At alpha equal to 0 degree, your TCR is in full operation. And what is inductive reactance? Inductive reactance is minimum, and inductive TCSC reactance, which is a function of alpha, it is equal to XL into XC divided by XL minus XC. And what is XL? XL is equal to omega L. And at alpha equal to 0 degree, the TCR is in full conduction and its reactance, inductive reactance, is minimum. And how much is that? Omega L. At alpha equal to 90 degrees, it's blocking, and its inductive reactance is infinite. But at alpha equal to 0 degree, it's in full conduction and inductive reactance is minimum. And what is the overall TCSC reactance? It is XL into XC divided by XL minus XC, and it is inductive in nature. So therefore, alpha C lim to 0 degree, this region, this range of delay, within this range of delay angle, your TCSC behaves in the inductive region as a variable inductive reactance or as a variable inductance. So therefore, within this range, your TCSC behaves as an inductor, variable inductor. So this is inductive region. And what is the range of delay angle? Delay angle range is 0 less than or equal to alpha less than or equal to alpha L lim. This to this. Okay. I hope this is clear. So therefore, this shows the capacitive mode of operation. This is the capacitive mode of operation below, and above it shows the inductive mode of operation. Okay. So therefore, it is very much clear that if you want to operate your TCSC in the capacitive region as a variable capacitance, the delay angle range is alpha C lim less than or equal to alpha less than or equal to pi by 2, and it acts as a variable inductance, variable capacitance, you can see. And if you want to operate the same TCSC in the variable, as a variable inductor in the inductive range, then the range of delay angle has to be 0 degree to alpha L lim, 0 to alpha L lim, and it acts as a variable inductive reactance, variable inductance. And this, within this range, that is alpha L lim to alpha C lim, you should not operate your TCSC at all, because this, within this region, resonance condition occurs, and at resonance, the inductive reactance or capacitive reactance, that is TCSC reactance, becomes infinite, and no transmission line current flows. Reactance becomes infinite. So this is the prohibited range, and this range is from alpha L lim to alpha C lim. Alpha C lim. So you should never operate your TCSC within this range, because it is the prohibited range. It's the range very close to parallel resonance. So I hope this is clear. This is how TCSC, with the help of these characteristics, I hope it is now clear how TCSC behaves as a variable compensator, as a variable capacitor, or as a variable inductor for different ranges of delay angle. Okay. Now, operating principle, we can discuss a bit in details. Operating principle is something like this. Let us assume that this is the situation. The current, transmission line current is like this. This is the transmission line current. If this is the capacitor, what will be the capacitive voltage? In a capacitor, current leads the voltage by 90 degrees, or capacitive voltage VC will lag behind current by 90 degrees. So it will be something like this. When current is 0, the capacitive voltage will be maximum. Capacitive voltage will be maximum. And when current is maximum, capacitive voltage will be minimum. So it will be something like this. This is VC, capacitive voltage. You can very clearly see that this this voltage current leads the voltage by 90 degrees because it's a capacitive circuit. Okay. Now, since we don't have a capacitor alone, we have a TCR switch also. I mean, this capacitor is shunted by a TCR. We can turn on this TCR at any instant of time. Let us suppose we turn on this TCR at this instant. Say, for example, at this instant, I will turn on TCR alpha. Alpha is the delay angle. I delay the turning on of TCR by this. You know that TCR is turned on, alpha is measured from peak of the voltage. This is the peak of the capacitor voltage, and same voltage gets impressed across TCR because it's in parallel with the capacitor. And from the TCR theory, you know that alpha, that's delay angle or firing angle, is measured from peak of the voltage across TCR. That is peak of the capacitor voltage. Let us assume we turn on or we fire the TCR after a delay of this much, maybe 20, 30 or 40 degrees. Okay. Let us see what happens. Equivalent circuit will look like this. This is capacitance. This is voltage across capacitance. And equivalent circuit will look like this. This is IL, which is a function of alpha. This is transmission line current I. And this is IC, which is a function of alpha, which is equal to I plus IL alpha. Now, let me draw this waveform again somewhere, say here. I will again draw the transmission line current. This is transmission line current I. And this is the voltage. For example, this is the voltage. This is the voltage across the capacitor. This would have been voltage across capacitor if only capacitor was there and it was not bypassed by TCR. So at this instant, I have already told you we will fire TCR somewhere here. Say somewhere here we will fire our TCR after a delay of alpha. We are issuing firing pulse to TCR. What is the capacitor voltage here from here to here? Capacitor voltage is negative. Current is positive. Current is flowing in this direction. But previously capacitor was negatively charged. So capacitor voltage is maximum negative here and then it decreases. So at alpha, capacitor voltage is negative. Negative voltage means it will not be plus minus like this. This plate will be positive. This will be negative. Negative capacitor voltage. And we have to fire the TCR. Which switch should get firing pulse? Now, since capacitor is charged like this and when TCR is fired, the capacitor will discharge through this TCR like this. So which switch has to be fired? Since this capacitor voltage is positive, the current has, when this TCR is turned on, current has to flow like this through this parallel LC circuit. So switch T2 has to be fired. So T2 will be issued firing pulse. So this is our switch S. So that will turn on the switch S. As soon as here, after a delay of alpha electrical degrees, switch T2 is issued firing pulse, it immediately turns on and आपका switch close हो जाता है. And what happens? This capacitive current flows like this. I mean, it discharges first and then capacitor starts charging with the reverse polarity. And as soon as this, it becomes a parallel resonant LC circuit. And we know that in a parallel LC circuit, tank circuit, when current flows between capacitor and inductor, see, this capacitor will discharge first and then it will quickly charge to a higher voltage with reverse polarity. That is the basic operating principle of a parallel LC circuit. Okay, so therefore it will not, the capacitor voltage will not follow this path. It will immediately, I mean, it will, as soon as this thyristor valve is turned on, T2 is turned on, S closes, capacitor immediately first discharges, it very quickly discharges, and then it charges with reverse polarity, okay, to a higher voltage, it charges with reverse polarity to a higher voltage. So this is the higher voltage to which it will charge. It will discharge and then it will charge to a higher voltage. Okay, so discharges and it charges like this. And then we know that its peak will be somewhere here. It will reach peak value somewhere here, और ये peak value पे पहुंचेगा, और we know that then it will start decreasing like this, और ये आपकी capacitor voltage, let's call this VCO. So therefore capacitor gets charged to a higher voltage. Normally if only capacitor was connected, this would have been the capacitor voltage, this would have been the capacitor voltage. But with TCR and firing the TCR after a delay of alpha electrical degrees, it causes discharging of this resonant current flows through this LC parallel circuit. Capacitor quickly discharges and then is charged quickly to a higher voltage with reverse polarity. Here it was negative, now here it is positive, and then as the positive current I flows through the capacitor, it keeps on charging to higher and higher voltage till I equal to 0, because we know that in a capacitive circuit, when current is 0, the voltage across capacitor is maximum, it reaches the maximum value. So you can see normally the maximum voltage would have been this much, but with this TCR turned on after a delay of alpha, it gets charged to a higher voltage, much higher voltage than the normal peak voltage, normal higher voltage. Okay, and you can see during this period, agar aap TCR current draw karoge, I mean this direction of current is taken as positive TCR current, and this direction of current through the TCR is taken as negative TCR current. And since thyristor T2 is turned on, capacitor discharges, so a negative current flows. TCR current agar aapko dikhana ho, so I can show that TCR current, I can show that TCR current yahan se yahan tak, agar TCR current dikhani hai, IL alpha, it is in the form of a pulse. क्योंकि होता क्या है, when TCR turns on, capacitor discharges, और जब capacitor completely discharge होता है, इसकी voltage 0 हो जाती है, and then capacitor starts charging with the reverse polarity like this, okay, or then after some time this thyristor switch, when the current, this TCR current IL alpha, when it becomes equal to 0, the switch automatically naturally commutates. It's the thyristor, it naturally commutates, it turns off. उसके बाद हम कोई firing pulse इसको issue नहीं करते, and we don't issue firing pulse in this half cycle to T1 also. तो आपका TCR off हो जाता है. It has done its job. Its job was to discharge the capacitor and charge it to a higher voltage with reverse polarity. That it does. उसके बाद capacitor charge होना शुरू हो जाता है, and it achieves a higher voltage than normal voltage. Okay, this is the TCR current. It's a small duration current. It is there for a small period of time. Okay, so therefore this clearly shows how a TCSC can produce a capacitive voltage higher than normal voltage by turning on TCR at a particular value of alpha. This alpha may be less than 90 degrees, because at alpha equal to 90 degrees TCR is off. ये तो off ही है. At alpha equal to 90 degrees, सारी current capacitor में flow होती है, तो ये situation है. This is the capacitor. And after say for example alpha equal to say 75 degrees, you turn on your TCR. आप TCR को on करते हो. Say somewhere here, TCR on हो जाता है. Alpha is less than 90 degrees, and I have already told you that the capacitor first discharges, then because of LC circuit it charges to a higher voltage, and then the capacitor voltage VCO is greater than the normal capacitor voltage VCO. Okay, and this is the TCR current in the form of a small duration pulse, current pulse. Okay, now let me show you complete positive half cycle and negative half cycle. Then it will be very much clear to you. This is switch. I will first of all show the transmission line current. So for example, this is transmission line current I. Okay, and आपकी voltage जो है, transmission line voltage would have been something like this, peak, and then something like this, capacitor voltage I mean. This would have been your capacitive voltage if alpha was 90 degrees. For alpha equal to 90 degrees, TCR is off. Its reactance is infinite. All the current flows through the capacitor. This is capacitor current and this is capacitor voltage. But what happens after a delay of alpha electrical degrees, say somewhere here, what we do? We turn on TCR. Since capacitor voltage is negative, which TCR will turn on? Negative means it is plus minus like this. Which device of this TCR, the switch has to be turned on? T2 is turned on. So T2 is given firing pulse, it immediately turns on. और ये जब on हो जाता है, the capacitor very quickly discharges and charges to higher voltage. It discharges first and then it charges to higher voltage. उसके बाद since current, positive current is continuously flowing, इसकी voltage बढ़ती जाएगी. Its voltage will keep on increasing like this. And during this period, if you draw the TCR current, omega t, and I will draw ITCR or IL, which is a function of alpha, यहाँ से यहाँ तक आपका TCR switch T2 on हो रहा है, and during this period capacitor first quickly discharges, its voltage becomes 0 and then it charges with reverse polarity. और जब आपका ये आपकी TCR की current है, and when TCR current becomes 0, this direction of current is taken as negative, the thyristor switch T2 turns off और आपका TCR भी off हो जाता है. So TCR की current in the form of a short duration pulse है, like this. और यह आपकी capacitor voltage है, you can call this VC or VC naught. Negative half cycle फिर current का जब आता है, उसमें भी आपको in the positive half cycle of current you have fired your TCR somewhere here. Similarly, in the negative half cycle of current, symmetrically you will fire your TCR somewhere here. Now, negative and negative half cycle of current is there. What is voltage? ये negative half cycle है. Current का. What is voltage? You can see voltage is, this is current, negative half cycle, and this is voltage. Voltage is positive. Positive voltage means आपका capacitor up, it's charged with this polarity. So therefore, if you want to turn the TCR on, current has to flow in this direction क्योंकि capacitor को discharge होना है. It's with this polarity, positive polarity. And which thyristor switch of this bidirectional switch has to be turned on for making current to flow in this direction? T1 has to be turned on. तो यहाँ पे firing pulse मिलेगी thyristor T1 को. So T1 will quickly turn on, capacitor quickly discharge करेगा और फिर recharge करेगा with negative higher voltage. अब आप देख सकते हैं, it's very interesting to see. The capacitor will very quickly discharge. यहाँ पे आप fire कर रहे हैं, पहले ये, it will very quickly discharge यहाँ से यहाँ तक. Let's say this instant to this instant, or this instant to this instant. It will, instead of firing it here, let us fire it somewhere here. Sorry, somewhere here. So it was earlier discharging, and then as soon as thyristor switch T1 is turned on, TCR turns on, capacitor quickly discharge. ये देखिए quickly discharge करेगा. और उसके बाद since current is negative, ये charge होगा with reverse polarity, higher voltage. ये higher voltage पे charge होगा, higher voltage, and then it continues. Previously also आप कह सकते हैं that it was charged to higher voltage, and this is how VC becomes VCO. And during this period, you can see you have turned on thyristor, this TCR thyristor switch. Okay, current is now flowing in this direction, and this direction of current is taken as positive. ये आपकी TCR current है, IL alpha. And as soon as current becomes equal to 0, and TCR, this thyristor T1 naturally commutates, and you do not fire it. So therefore, in the next positive half cycle of the current, you will again turn on thyristor T2 after this delay, and then in negative half cycle of current, you will turn on thyristor T1, and you will keep doing this if you want to maintain this capacitor voltage constant. But if you want to change this capacitive voltage, you want to make this TCSC as a variable capacitance, then you can change alpha. Alpha 90 degrees से आप कम कर लो till alpha C lim. At alpha C lim आपकी capacitive voltage maximum हो जाएगी, because TCSC reactance becomes maximum. Just go through this. TCSC reactance is maximum here when alpha is equal to alpha C lim. At alpha equal to pi by 2, it is minimum 1 by omega C. Then as you decrease alpha towards alpha C lim, capacitive reactance increases and becomes maximum here. And when alpha is equal to alpha C lim, decrease कर रहे हो alpha 90 degrees से alpha C lim तक, your TCSC capacitive reactance goes on increasing, and capacitive voltage will also keep on increasing and increasing. उसके बाद अगर आपको इसको इंडक्टिव रीजन में ऑपरेट करना है, so you have to operate from alpha L lim to 0 degree. And if you decrease this alpha L lim towards the 0 degree. 0 degree means यहाँ तक, ये 90 degree है, ये 0 degree है. I mean आप 0 degree तक इसको ये करो, you decrease it up to 0 degree, you will get similar waveform, but voltage will lag behind current, because your TCSC will behave in the inductive region, okay, variable inductance. Anyway, this is the capacitive current. This is the capacitive current. Sorry, this is the transmission line current, not capacitive current. This is the transmission line current. And you can see what is capacitive current. Capacitive current is I plus IL alpha, or capacitive current is same as transmission line current जब तक आपका TCR ऑफ है, और जब TCR ऑन हो जाता है, TCR की करंट IL अल्फा है, उस केस में what is the capacitive current? It becomes IL plus IL alpha. So यहाँ से यहाँ तक आपकी capacitive current I नहीं रहेगी, it will be I plus IL alpha. तो ये इसको ऐड हो जाएगा, ये ऐड हो जाएगा. So this is capacitive current IC alpha equal to I plus IL alpha. देखिए यहाँ से यहाँ तक और यहाँ से यहाँ तक पॉजिटिव हाफ साइकिल ऑफ ट्रांसमिशन लाइन करंट में कैपेसिटिव करंट इज सेम एज ट्रांसमिशन लाइन करंट, बिकॉज TCR इज ऑफ. TCR ऑन होता है फॉर दिस वेरी स्मॉल पीरियड एट अल्फा, बिकॉज TCR करंट इज इन द फॉर्म ऑफ शॉर्ट ड्यूरेशन पल्स, एंड ड्यूरिंग दिस पीरियड व्हाट इज योर कैपेसिटिव करंट? इट इज I plus IL alpha. I is this, उसको IL alpha ऐड कर लीजिए, so this becomes your IC alpha, which is I plus IL alpha. Similarly, negative half cycle में your capacitive current is same as transmission line current, लेकिन यहाँ से यहाँ तक आप देख सकते हैं क्योंकि TCR current flow होती है, आपकी capacitive current ये हो जाती है. It is IC alpha equal to I plus IL alpha, because during this period IL alpha is also there. So this shows capacitive current, and this clearly shows the operation of a TCSC as a variable capacitance for a delay angle range from 90 degrees to alpha C lim. If delay angle range is alpha L lim to 0 degree, then you will get similar waveforms, I mean variable voltage, but that voltage will be inductive voltage. Your TCSC will operate in the inductive mode of operation. So therefore, for this range of delay angle, it will operate as a variable capacitive reactance, and for this range of delay angle, it will operate as a variable inductive reactance. Okay. So this explains the operation of TCSC. More on it in next class. I request and I advise all of you to go through this lecture, and in case of any doubts, please feel free to ask. All the best to all of you. Thank you.